It's my honor to give the keynote in this workshop. Let me play a pre-recorded talk for about 20 minutes, and then I can answer any questions you might have. So let me share the screen.
Hi, everyone. I'm Professor Jerry Chou from National Tsing University. It is my honor to be invited for giving this.
Hey, we can hear it now.
You cannot hear?
No, we can hear it. It's okay.
Okay. Then I'm gonna play. Okay, here.
The topic I would like to share today is the recent events and future challenges for network function virtualization infrastructure. In this talk, I will first explain what is network function virtualization and introduce its terminologies and architecture. Then I will talk about its recent events and challenges. Specifically, I will focus on two of the most important topics right now: the VNF resource allocation problem and the idea of cloud-native network function. Finally, I will briefly discuss the role of MFV to other applications such as software-defined network, 5G, and Internet of Things, followed by the conclusion. So first of all, what is network function virtualization, or MFV? In short, it is a way for network providers to design, manage, and deploy their network infrastructure using virtualization technologies. As we know, the mission of network providers is to provide network services to their users. These new network services often compose of a chain of network functions, such as load balancer, DNS, or firewall. So network service is also referred as a service function chain. Traditionally, these network functions are provided by proprietary physical hardware or metal box, which can be expensive, inflexible, and vendor specific. But under an MV and with the help of virtualization, we now can virtualize these network functions into software programs, which can be deployed and running on general purpose commodity servers in a standardized and open environment. Therefore, we basically can obtain all the benefits of virtualization comparing to using physical resources. That includes the ability to manage more devices, change network architecture on the fly, enable seamless deployment of new services, and dynamic scale resources to deal with the service workload changes. Resource utilization can also be improved by consolidating multiple virtualized network structures on a single physical machine. Last but not least, standardized MFV software interface allow network functions to be implemented as a modular part. Hence, VNF has become a crucial technology for future network services because it can reduce the need for hardware equipment, avoid vendor blocking problems, simplify network operations, and lower the cost of capital expenditure and operating expenses. All of these benefits are highly desired by network providers. However, to transform the existing network architecture to MFV is not an easy task. We have to define and build the infrastructure for deploying and managing MFV. And many open questions must be answered before the MFV solution can be realized in practice, such as how the physical network function can be virtualized, how VNF can be deployed or managed to ensure resource efficiency and service quality, and how to support operations like service migration, reconfiguration, and monitoring. So MFV is still an active and urgent research topic that has drawn growing interest from both academic and the industrial communities. One of the important milestones is the MFVI architecture proposed by ETSI, Europe Telecommunications Standards Institute. The architecture composed of three parts: infrastructure, service, and management. Let me briefly introduce them in the next few pages. Service has the following components. On the top are the OSS and the BSS, which are the supporting subsystems for operating and business, such as pool management, configuration management, customer management, ordering management, etc. beneath it is the virtual network function, or VNF, which is the basic block that provides services. And each of individual VNF instances is managed by an element management system to handle its functional management issues. Next in the bottom is the part of infrastructure. It refers to all the hardware and software components that build up the environment for deploying VMware. Similar to cloud platform and infrastructure, it contains a virtualization layer to provide virtualized resources for computing, storage, and networking. However, VMware brings many new challenges, especially for security and performance. So new virtualization technologies and architecture are still required to address these issues. The recent development of CMF that we will talk about is a good example of that. Finally, and most importantly, is the management and orchestration component. It is also called Mono. It plays the key role for managing all the components from top to bottom in order to realize the OFB solution. That includes to orchestrate the VMF to form a network function service chain, to manage the VMF lifecycle from installation to termination, and to orchestrate infrastructures to deploy VMF on virtualized resources. Therefore, the management policies and strategies designed in Mono often determine the cost performance of the whole service platform. Clearly, there are many challenges that needs to be solved in each component. But in general, industry is making greater efforts on service and infrastructure in order to build up the whole architecture. On the other hand, Mono involves more algorithm and strategy design for optimization. So we have seen more research work from academia to discuss the design of Mono. In this talk, we share some of the most important recent advances for each of these two communities. For service and infrastructure, that is the emerging technology called cloud-native network function. And for management, that is the well-known VMF resource allocation and placement problem. So let me begin with the VMF resource allocation problem. The VMF resource allocation problem can be further divided into 3 steps: chain composition, for word graph embedding, and request scheduling. First, in chain composition, network operator can explore the flexibility introduced by virtualization to dynamically compose the chain of VMF and adjust the resource allocation of its edge and nodes. Therefore, given a set of user-defined service requests, which require for various network functions and traffic load, we need to convert them into a set of service function chain with resource demands. For example, the service demand given in the left side can be served by 2 different service function chain options. Next, given a set of service function chain from the previous step, we need to map the VMF functions to physical node and map the service chains to physical links. The service function chains can be described as a virtual network graph, and the physical network topology can be described as a physical network graph. So the problem is often called virtual network embedding or VMF placement problem. The VMF placement problem is also the most critical challenge and extensively studied problem in Mono, because it has significant impact to the resource usage efficiency and the service quality. In general, the problem is formulated to maximize or minimize service operation objectives and subject to a set of resource and service constraints. However, it is proven to be an incomplete problem. So the problem complexity grows exponentially to the scale of networks and number of service function chain or network functions. Even more difficult, the service request and traffic workload can change over time. Therefore, the problem must be solved in a timely manner as well. To tackle this challenge, people define the basic model of the systems, such as resource and energy consumptions, and the service revenue or quality. Then either formulate the problem as an ILP problem and obtain a near optimal solution using ILP solver, or propose heuristic algorithm based on greedy decision or apply meta-heuristic search optimization methods. Finally, traffic predictor or monitoring techniques have also been discussed to trigger the placement reconfiguration. So the traffic variation can be handled proactively or reactively on the fly. Finally, virtualization allows multiple BMF to be consolidated on a single node. So resource sharing problem on the node must be also addressed. And it can be considered as a time sharing task scheduling problem to decide the scheduling order and the priority among service requests. The problem can be more difficult than the general scheduling problem because the flow dependency and the service using Linux container instead of virtual machine.
Okay, my guess.
Network function. The biggest difference between container and virtual machine is that container virtualize OS layer, not hardware layer. So containers may have isolated OS environment, but they could share the same OS. This allows containers to have benefits like higher deployment density, low virtualization overhead, fast deployment time, and enable microservice architecture. Therefore, we have seen a growing trend to migrate VMF from virtual machine to container. And even hybrid infrastructure that combines virtual machine and container together has been proposed in order to address some of the weakness of containers, especially on performance isolation and security. But this transition is not trivial because virtual machine and container are different virtualization technologies, and each of them have their own software architecture and management orchestrator. For containers, the most popular orchestrator is Kubernetes, developed by Google to manage their data centers and cloud services. It abstracts away the underlying hardware and provide a uniform interface to deploy and manage loosely coupled distributed applications, in particularly microservices. More importantly, Kubernetes provides a container network interface that supports plugins to configure network interfaces in its containers. So different networking virtualization and management techniques can be implemented and available for containers. Plugins like Modus, Patio, Cilian are all commonly used in CMF solutions. The main purpose of these plugins is to enhance network performance and manageability, especially on packet processing. Traditionally, physical network functions rely on special purpose hardware like ASIC. But now we have to implement these functionalities in software program running on commodity servers. As we know, software can be more flexible, but also slower than hardware. So how can we overcome this limitation? The solution can be divided into hardware-based and software-based. The basic idea of a hardware-based solution is to offload the computing-intensive operations to hardware accelerators like NPU, GPU, or FPGA. On the other hand, Software-based solutions explore all kinds of software techniques and architecture to minimize the overhead, OS kernel, and context switch. We briefly introduce a few as below. SRIOV is a well-known virtualization technique that allows VM to directly manage virtualized I/O devices without involving the host OS. It has become an industry standard, but it still requires special hardware support and only can be used for virtual machine. Next is PPDK. It provides libraries to offload packet processing workload from kernel space to user space and eliminate the performance overhead of kernel interrupt. So many packet acceleration solutions are implemented using PPDK. For example, FDIO is an open source implementation of the Cisco's vector packet processing technology. These solutions can be used for both virtual machine and content. Last but not least, there is a growing interest to develop solutions based on eBPF, which is a feature in modern Linux kernel that allows you to write mini programs that are attached to low-level hooks in the Linux kernel. Its architecture is particularly convenient for implementing packet management services for CMF. So both Calico and the Cillian CMI are based on these techniques. Finally, besides the differences in orchestrator and virtualization, packaging network functions into CMF is considered to be more challenging than BMF because the cloud-native service function should be stateless and loosely coupled microservices that often require further re-architecting of network function software. Because traditional software programming tends to store the state locally and have no natural boundaries between function codes for decomposition. Furthermore, traditional application is based on procedural configuration, but container orchestrator like Kubernetes is based on declarative configuration. So CMF must be consistent checking of entire configuration before any change is applied. Therefore, existing BMF implementation cannot be directly packaged into CMF. Finally, I would like to mention how NFV and other network technologies are related. First is SDN, Software-Defined Network, which has been discussed for many years before the emergence of NFV, and it has been widely deployed in many data centers and enterprise clusters. It shares many common goals with NFV, and also aims to use software to manage networks. But it focuses on separating the control plane from the forwarding. In contrast, NFV is to further decouple network functions from proprietary hardware appliances. So there are strategies and architectures at different levels. Hence, people have to attempt to combine the two together to deploy SDN on top of NFV as well. Next is the relation between NFV and 5G. As we know, 5G is another popular topic in recent years. It contains many new networking technologies in order to deliver lower latency and higher bandwidth for wireless communication. One of them is the idea of Cloud WAN, which aims to softwareize radio access network and create a centralized BBU pool to coordinate remote radio heads. Many practitioners and industry companies have proposed the idea to use SDN and NFV as the foundations to build such cloud WAN architecture. Another key idea in 5G is network slicing. The idea is to divide single network connection into multiple distinct virtual connections. So each virtual connection can be managed separately for different types of traffic, such as IoT, end-to-end communication, mobile applications, or self-driving cars. Consider each virtual connection as a service function chain request. Network operator can now leverage NFV to deploy and manage these networks with sufficient agility and efficiency. To conclude my talk, without a doubt, DNF has emerged as a crucial technology for future networking. Many challenges and open questions remain and require collective efforts from researchers and practitioners. such as the BNF resource allocation and the CNF problem mentioned in this talk. Many new ideas like combining BNF and CNF have also been explored recently as well. And while the BNF solutions are still under development, we already can see it will play an important role to drive the future technologies, including 5G, IoT, and self-driving cars. If you are interested in the topic today, you are welcome to read our papers published in this workshop. 2 papers will be presented this year. One of them proposes a hybrid BNF placement strategy, and the other one evaluates different performance acceleration solutions for CNF. Thanks for listening. If you have questions, please contact me by email.
I have some questions. For addressing many problems in VNF, like for replacement like that, you want to think about using IRP greedy heuristic algorithms like that. Would there be any room for using AI machine learning like that, or is there any specific reason why you are primarily considering those techniques?
Yeah, indeed. So the true form of the VNF placement problem is a graph problem, right? So especially, or you can see as optimization problem. So many techniques can be used in order to find the optimum solutions. For example, I did see some people propose to use deep learning, especially reinforcement learning, as the search algorithm to find the optimal solution. Yeah, so you can, for example, to be more specific, you can imagine like every action is to decide a placement, and you can use swapping, right? Keep swapping the pair, the placement of 2 network function until you reach some optimal result. So every action is a swap decision, and you can make the swap and evaluate, see how it affects the results, and interact with this search process and to find the optimal solution. Yeah. So indeed, we see some of those technique based on deep learning.
Okay.
Yeah.
Okay.
And also another example could be people also visualize the placement as a picture, because we know deep learning is better working with image, right? So I remember I also saw some people they visualize, basically represent the placement as an image, as a picture. Right, and to train the model to identify what kind of the pattern or the shape usually result in better results in terms of the optimization objectives, and try to recognize the pattern quickly as a way. So yeah.
Okay. And one more question is that for in your research, are you also considering like the security vulnerabilities in virtualization?
In my current research, not yet, but in our general survey, we saw quite a bit because it's a very important problem, and that's one of the main debate between VNF and the CNF. Basically the virtual machine-based or container-based virtualization. If you use virtual machine, then in general, people think it's secure enough. Also, of course, there's still some security hole, but it's particular issue for container-based virtualization, as we all know. So that's why in the talk, I also mentioned that's one of the direction people are working on. Is to basically develop some lightweight virtual machine. Yeah, so because we want to deploy those network functions very quickly. So using VM is too slow. So we do want to have a very lightweight virtualization technique with good isolation or good security. I think we already saw some of those solutions from, for example, from Amazon. They have a solution called Filecracker. So that's how they run some of the Docker or container image on those virtualization platform, proven to be very fast and more secure. So that's very important for CNF in the future.
Then in that Amazon platform, do they also have like detection and prevention protection tools there? Detection of like malicious activities or like some faulty actions like that?
So yeah, so if detection usually used to detect some anonymity or a malicious user behavior. I think that's also part of the issue for VNF management, because you deploy those network services for users, but you cannot fully trust the users as well, just like all the cloud services. So those kind of problems also exist for VNFI. They need to develop those monitoring or detection mechanism to monitor user behavior.
Any other questions? Actually, I've got one. First, let me thank you for your nice keynote presentation talk. And you said that the problem is in general NP complete. So it's quite difficult. It's hard to get an optimal solution. The question is, are there any relaxations that prove to be of practical use and that allows for polynomial time algorithm, for efficient algorithms? Thank you.
Very good questions. So in terms of the bound, I haven't seen it yet. It's basically a graph embedding problem. So I'm not sure there's any tighter bound or relaxation, not in my knowledge. But what I do know is in practice, especially in industry, they simplify the problem by consider simpler network topology. So as you can imagine, the reason it's so hard to solve is because if you want to map two arbitrary graphs, embedding them together, then it's a very complicated problem for sure. But in the industry, they can build a peer-to-peer or pairwise connection between all the servers. Then in that case, actually, it doesn't really matter where you place those network function, because their hop count is the same. It's one hop, no matter where you place it. So that is actually we found out in the survey, some white paper proposed by the company. They say that's how they address this issue. They build those pairwise connection network in the physical layer. So in the virtual layer, when you place it, it's only a matter of problem. How many instances do you need for a certain network function? Where you place, it doesn't really matter. So that's how we find out. Very interesting how they can solve it. Yeah.
Thank you very much.
Thank you.
I have another question. Thanks for the nice presentation. What do you think it will take for these technologies to be adopted widely in the industry?
Actually, it's already get adopted. Yeah, I'm pretty sure like AT&T or China Mobile, or those big network operator, they already at least experience it and deploy for some region. And that's what I heard. But just like the example I give you, they try to simplify the problem, at least in terms of the management layer. Right now they are more focusing on just to virtualize the hardware build to implement the virtualized network function as a container or virtual machine or a package into a virtual machine. That's what they are working on. And if you search online, you already can find several virtualized network functions. For example, for firewall or packet inspection. So people already implement it, and they can deploy it using OpenStack, traditionally, or right now they are experienced with Kubernetes. So that's what I know, but probably not in a very large scale. And like everyone mentioned, the security problem, there are still some concern for the infrastructure.
Thanks.
Thank you.
Any other questions? Okay. Thank you, Dr. Chou, for excellent presentation, your keynote speech.